Hello students, welcome back. In this video we are going through Chapter 5, Section 2, Binomial. So a binomial probability distribution results from a procedure that meets four requirements. So there are four things that must be satisfied before we have binomial. Number one, the procedure has a fixed number of trials, and a trial is just a single observation. The trials must all be independent, meaning that the outcome of any individual trial does not affect any of the other trials' probabilities. Number three, and this is really the important one that makes it different from a lot of other requirements. Each trial must have all outcomes classified into exactly two categories: success or fail. Yes, no, right, wrong. There cannot be different outcomes other than those two. So if you flip two coins and you want to know how many heads you have, that's not binomial because that would have three categories of outcomes: either no heads, two heads, or one head. So this needs to be exactly two categories for all of its outcomes. And then four, the probability of a success remains the same in all trials. So we talk about the two outcomes as success and failure, even if a success doesn't actually mean, like, in the context of what you're looking at, it actually is a success. We just say success is just and failure, just the two outcomes that we call them. Those are just the two categories. It's just terminology. I don't want to confuse you with that. I probably just did. But let's continue. So the probability of success is going to be lowercase p, and the probability of f is q, which is the probability of a failure. And remember that the probability of failure is going to be 1 minus p, and then vice versa. Probability of success is 1 minus q, since these two are complements of each other. Some other notation: n is the number of trials, x is number of successes in n trials, p is probability of success in one trial, and q is the probability of failure in one of the n trials. And then p of x is the probability of getting exactly x successes among the n trials. All right. Without further ado, let's look at an example. When an adult is randomly selected, there is a 0.85 probability that this person knows what Twitter is. Suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. So we want to know exactly 3 of 5, not 3 or more or anything else, exactly 3 of 5. So part A is, does this procedure result in a binomial distribution? And if so, identify x, n, p, and q. So let's look at the four requirements. So the first one says that you need to have a fixed number of trials. We have 5 trials occurring, so yes. The 5 adults are independent, because the probability of any adult knowing Twitter is not affected by the results of anybody else. So yes, they are independent. Each of the 5 trials has 2 categories for outcomes. Either they know what Twitter is, or they do not know what Twitter is. So we'll say that knowing what Twitter is a success, and not knowing what Twitter is a failure. So 3 is satisfied. For each randomly selected adult, there is a 0.85 probability that they know what Twitter is. So that will remain the same for all the peoples. So yes, all 4 requirements are satisfied. So now we can say what x, n, p, and q are. So n equals 5, since we're doing 5 trials. We want to know exactly the probability of getting 3 adults. So x is equal to 3. That's the number of successes in n trials. The probability of success is going to be a person knows what Twitter is, so p equals 0.85. And the probability of failure, which is someone not knowing Twitter is going to be 1 minus 0.85, or 0.15. So here is your very simple formula for doing binomial probabilities. well, it's not that bad. That was sarcasm, but it's really not that bad. It's n factorial divided by x minus n factorial times x factorial multiplied by p to the x multiplied by q raised to the n minus x. But we are not expecting you to do this formula. We will use technology to get those values. So here's how we do it using the calculator. I gave you a little quick YouTube link as well. Here are the step-by-step instructions. But let's do it together with the calculator. So let me pull up the TI-84 and let's look at the instructions. I wish I was able to. I don't know. I can't split it in a good way. All right. So press second and then press vars. So I'm going to hit the little second and then I'm going to hit vars. And then I'm going to scroll all the way down to binomial PDF, not CDF. Make sure you don't do that. So do binomial PDF. So I want to know the number of trials that I'm dealing with. I'm dealing with 5 trials. The probability of success is 0.85. And I want to know getting exactly 3. So I'm going to enter that, hit enter again, and I get a 13.8% probability. That's using the TI-84. You can also use StatCrunch as well. So you're going to hit stat, calculator is binomial, and then type in the values as indicated, and then you'll get the same answer as well. Whoop. Let me go back to viewing the slideshow. So let's go back to the Twitter example. Given that there is a 0.85 probability that a randomly selected adult knows what Twitter is, use the binomial probability formula to find the probability that when 5 adults are selected, exactly 3 of them know what Twitter is. That is, find P of 3, given n is 5, x is 3, P is 0.85, and Q is 0.15. Here is the formula right here. And when you do it with the formula, you get 0.138, but we are going to be using technology, which gave us the same value of 0.138. And one thing to note is that if you did this 5 different times, the probability of getting exactly 1, plus the probability of getting exactly 2, plus the probability of getting exactly 3, which is just right here, plus exactly 4, plus exactly 5, you'll get 100% because it's either you have it or you don't. So by looking at it 5 different times, you're giving it all the possible scenarios. Just a little thing to note. All right, let's do another example. Based on a Harris poll, 60% of adults believe in the devil. Ooh. Assuming that we randomly selected 5 adults, use table A1 to find the probability. What's table A1? Okay, so this is an important distribution table that we will be using for the rest of the course. This is the first time you're being introduced to this, at least that I remember. So A, the probability of that exactly 3 of the 5 adults believe in the devil. B, the probability that the number of adults who believe in the devil is at least 2. And then C, the probability that the number of adults who believe in the devil is less than 2. So let's look at the difference. Part A is very similar to the last example. 3 out of 5 adults believe in the devil. B is saying at least 2, which means 2 or more, which means I have to do the probability of 2 plus probability of 3 plus probability of 4 plus the probability of 5. And then 2, less than 2, is just going to be the opposite. It's going to be either 0 or 1. So it's a little bit of a different type of problem, parts B and C are, than the previous example. So we can do this with technology as well. We're going to do second vars, go to the binomial PDF, and enter as follows, and we get 0.3456. Part B is saying at least 2 means that the number of successes can be 2, or 3, or 4, or 5. So you're going to have to add all of those up. And then you're going to get 0.913. So there's a 0.913 chance that at least 2 people out of 5 believe in the devil. And then finally, part C is the phrase less than 2 means that the number of successes is 0 or 1. So add those 2 possibilities up, do the binomial probability 2 more times, add those values together, and we get 0.087. And as a quick check, the only 5 possible outcomes are 0, 1, 2, 3, 4, 5 successes. So these 2 parts B and C encompass every possible outcome. So if you add up these 2 values, you should get 1, or 100% of all the outcomes. And when you check it, you do get that. So we need to use mean and standard deviation for critical thinking. The mean is going to be mu is equal to n times p. The variance is going to be sigma squared times npq. And the standard deviation is going to be the square root of that. So then what makes something significantly high or significantly low? And it's going to be that p of 0.05 being that magic number. So if the probability of x or more successes is 0.05 or less, we would say that's significantly high. And then the opposite true. If x successes among n trials is significantly low, the probability of x or fewer successes is 0.05 or less. Some of the rationale for this is just kind of showing you where the equation is coming from. And this portion of the equation is giving you the number of possible outcomes. Notice it looks very similar to some of the counting formulas we did in chapter 4. And then right here is just going to be the probabilities of the multiplication counting rule. So it's the probability of x successes among n trials for any particular order. So the probability of success is going to be p to the x power for however many times you want to have a success. And then q is going to be how many times a failure raised to how many times you failed. How many times you fail is going to be n minus x. So that's the rationale for it. One quick thing I want to say is in this problem, I talked about table A1. I forgot that I'm going to introduce this in a little bit, just not quite yet to use it for that. So kind of ignore that in the context of this for now. And that concludes Chapter 5, Section 2. Any questions, let me know. Thank you.